Today's mission is to understand time. Thanks to Google AI, scientists, web developers, and YouTube, we can explore subject of time in a profoundly interesting way. Here we go. Speed of light in a vacuum is constant for all observers, regardless of their own motion. Time is relative. It can appear to pass at different rates based on observers' motion and gravity, a core concept in Einstein's theory of relativity. Gravity affects time. Stronger gravitational fields cause time to slow. For example, clocks on Earth's surface run slightly slower than those at higher altitudes. The closer an object to a massive body, the deeper it is in the gravitational well, and the more pronounced the time dilation effects become. Speed affects time. The faster an object moves, the slower time passes relative to a stationary observer. This effect, known as time dilation, becomes significant as speed approaches the speed of light. There is no absolute time. Relativity shows that time is relative to the observer's frame of reference. Time and space are interconnected. Einstein's theory united the time and space into spacetime. Flow of time is linked to entropy. The arrow of time is thought to originate in the Big Bang. As entropy increases, time moves forward. It is why a broken egg is impossible to reassemble. The arrow of time points in the direction of increasing entropy, other words disorder. When time is measured by celestial events, things to consider. The Sun, along with the entire solar system, is not static but in constant motion within the Milky Way galaxy. Speed and orbit. Speed. The, the Sun orbits the center of Milky Way at impressive speed of approximately 220 to 250 kilometers per second, or roughly 483,000 miles per hour. Galactic year. Even at this tremendous speed, the Sun takes astonishing 225 to 250 million years to complete one full revolution around the galactic center. This duration is sometimes referred to as galactic year. Orbital path: elliptical and oscillating. The Sun's orbit around the galactic center is not a perfect circle, but rather slightly elliptical, according to Forbes. Additionally, the Sun bobs up and down through the plane of the galaxy's disk, similar to a cork on water, completing one such oscillation roughly every 60 to 70 million years. This results in a helical or spiraling path through the space as the Sun and the Solar System orbit the galaxy. Influence of other stars. The Milky Way contains billions of stars, and their gravitational interactions contribute to the complex and slightly elliptical nature of the Sun's orbit. Position and plane. Location: the Sun is situated in Orion arm of Milky Way, approximately 26,000 to 28,000 light-years from the galactic center. Angle: the plane of our solar system orbits the ecliptic is tilted at the angle of roughly 60 degrees relative to the galactic plane. In essence, the Sun and the entire solar system are engaged in a long dynamic journey with the Milky Way, following an elliptical path and simultaneously oscillating through the galactic plane. This movement is consequent to the complex interplay of gravitational forces within our galaxy. The Milky Way is not alone, and is subject to the gravitational pull of larger structures in the universe, causing it to move and be influenced within its large cosmic environment. Within the local group, The Milky Way is gravitationally bound to other galaxies in its immediate neighborhood, forming what's called the local group of galaxies. The Milky Way and the Andromeda Galaxy, the two larger galaxies in this group, are actually approaching each other at roughly 120 to 130 kilometers per second. This is more of a mutual gravitational dance than one orbiting the other, and they are expected to collide and merge in several billion years. One smaller galaxy also orbits a common center of mass, barycenter, within the local group, according to the Love the Night Sky, towards the Great Attractor and beyond. The local group itself, including Milky Way, is being pulled towards a massive region of space known as the Great Attractor. The Great Attractor is a gravitational anomaly, a region of unusually high mass concentration, likely a supercluster or a convergence of several massive structures, located roughly 150 to 250 million light-years away in the direction of the Centaurus constellation. This gravitational pull causes the local group to move towards the Great Attractor at speeds of around 600 to 627 kilometers per second. Recent research suggests that the Milky Way and its neighbors are not only influenced by a Great Attractor, but also potentially by even larger structures like Shapley superclusters, which lies beyond the Great Attractor, according to Simple English Wikipedia. The Laniakea supercluster. The Great Attractor is now understood to be a core of an even larger structure called Laniakea Supercluster, which translates to "immense heaven" or "immeasurable heaven" in Hawaiian. This supercluster is a massive structure that includes the Virgo supercluster, where our local group resides, and spans across 500 million light-years, containing around 100,000 galaxies. Local flow within the Laniakea supercluster converges towards the Great Attractor, according to Wikipedia. In essence, the Milky Way is not orbiting a single grander subject in the way the planets orbit the Sun. Instead, it's caught in a multi-layered dance of gravitational influences, being pulled towards the Great Attractor, the core of Laniakea supercluster, and further influenced by the Shapley supercluster, all while rotating within the local group and interacting with galaxies like Andromeda. This indicated movement reveals the immense scale and dynamic nature of the universe. The arrow of time is the concept that has a fundamental direction, moving from the past to the future. This directionality is not inherent in the fundamental laws of physics, but arises from the way the universe is structured and evolves. The most accepted explanation for the arrow of time is related to the concept of entropy. The direction of time. Entropy. The thermodynamic arrow of time is driven by the second law of thermodynamics, which states that the total entropy, other words disorder, of a closed system always tends to increase. The arrow of time points in the direction of increasing entropy. Cosmological expansion. The cosmological arrow of time is defined by the direction in which the universe is expanding. As the universe expands, galaxies move further apart, leading to increasing disorder in the flow of time in the direction of expansion. Irreversibility. The arrow of time is evident in irreversible processes, such as dropped egg breaking or a shuffled deck of cards becoming disordered. These processes are natural and always occurring in direction of increasing entropy, making the reversal of time seems nonsensical to us. Motion of the Milky Way. The Milky Way, along with other galaxies in the local group, is moving away from other galaxies in the universe as a result of universe's expansion. It's also rotating around the center of the galaxy and moving within the local group, heading towards the Andromeda Galaxy. Relationship between the two. The direction of arrow of time in the Milky Way and the rest of the observable universe is consistent. Time flows forward and entropy increases regardless of the Milky Way's movement. The expansion of the universe, the cosmological arrow of time, established the direction of the arrow of time. This cosmological flow influences the local arrow of time, including within the Milky Ways according to the ScienceDirect.com. In essence, the Milky Way's motion follows the laws of physics within an expanding universe, where the arrow of time points towards the future and increasing entropy. Speed and entropy, while not directly proportional, are deeply connected through the concept of energy. Understanding this relationship requires exploring the second law of thermodynamics and the behavior of particles at the molecular level. Temperature and molecular motion. Entropy and temperature. Entropy is a measure of disorder or randomness in a system. Temperature, in turn, reflects the average kinetic energy of the particles within a substance. Higher temperature means particles are moving faster and more randomly, leading to a greater disorder and, therefore, higher entropy. Faster particles, more energy. Heating a substance increases the kinetic energy of its constituent particles, causing them to move at high speeds. This increased speed allows the particles to overcome intermolecular forces and spread out more, occupying a large volume and increasing the system's disorder. Phase transitions. Consider the transition from solid to liquid to gas. In a solid, particles are tightly packed and vibrate in fixed positions. As heat is added, the particles gain kinetic energy and vibrate more vigorously, eventually breaking free from forming a liquid. Further heating causes particles to move even faster, overcoming the forces holding them together as a liquid, and transitioning into a gas, where they move freely and randomly. This progression from more ordered to less ordered states is an increase in entropy, driven by increased particle motion. Speed and time dilation. Relativity and entropy. When considering objects traveling at relativistic speeds, approaching the speed of light, the effect of time dilation comes into play. According to special relativity, time appears to slow down for an object moving at high speeds relative to stationary observer. Frame of reference. This doesn't mean entropy stops at the speed of light, but rather that the rate at which processes occur within the moving system, including those that leads to increasing entropy, appears to slow down for the outside observer. An observer traveling within the system, however, would still experience time and entropy increases at the normal rate, as they are at the rest within their own frame of reference. Irreversible processes. Entropy production is intrinsically linked to the irreversible processes such as heat dissipation or friction, which converts the order energy into disordered thermal energy. When a system moves faster, the rate of these irreversible processes, and thus the rate of entropy generation, can be affected as observed from different frames of references. For instance, a new theory suggests a relationship between time it takes for non-equilibrium process to occur and the rate at which it generates entropy, implying the faster processes might require a higher rate of entropy production, according to the American Physical Society. Important caveats: not directly proportional, while increased speed of particles as in higher temperatures lead to higher entropy, the relationship is not simply linear proportionally. Entropy is a complex state function depend on various factors, including the system's volume and pressure, not just the speed of its particles. Overall versus local. It's crucial to distinguish between the kinetic energy of individual particles and kinetic energy of entire system. While the former directly affects the entropy at the microscopic level, the latter, for example car moving at a high speed, doesn't directly dictate the entropy of its individual components. In essence, speed and entropy are connected through the concept of energy distribution and molecular motion. Increased speed of particles, higher temperatures lead to increased disorder in entropy. At relativistic speeds, time dilation affects the observed rate of entropy increase, while the relationship is not one of the simple proportionality. Time measuring devices. While atomic clocks are the most accurate and are crucial for defining SI seconds, modern form of the metric system, International System of Units, physics utilize various other methods for measuring time depending on the scale and the context of their research. Here are some key ways. Astronomical observations, celestial events. Ancient civilizations relied on a regular movement of celestial bodies like the sun, moon, and stars to establish calendars and measure time. Earth's rotation. The rotation of the Earth on its axis, giving us the day and is fundamental measure of time. Britannica mentions universal time (UT) is based on Earth's rotation and is computed using observation of astronomical phenomena. Lunar phases. The phase of the moon also provide a natural way to track the passage of time. Sidereal time measures the time based on the apparent movement of stars and constellations across the sky, according to Wikipedia. Mechanical clocks include pendulum clocks and escapement mechanism. Pendulum clocks. The rhythmic swing of pendulum, with its relatively constant period, was a significant advancement in timekeeping. Quick and dirty tips notes. Christian Huygens is credited with building the first pendulum clock, and these devices achieved unprecedented accuracy compared to previous methods. Escapement mechanisms. These devices control the release of energy in small, regular intervals, allowing mechanical clocks to tick off the passage of time. Quartz clocks include piezoelectricity and quartz oscillators. Piezoelectricity: quartz crystals vibrate at a constant frequency when subjected to an electric field, a phenomenon known as piezoelectricity. Quartz oscillators: these clocks utilize the vibration of quartz crystals as their timekeeping element, achieving remarkable accuracy. Quick and Dirty Tips notes the first quartz clocks were accurate to within 5 seconds per month. Other physical phenomena include radioactive decay, atomic time, optical lattice clocks, and Planck's time. Radioactive decay: the decay of radioactive elements, though a random process, can be used to measure long-time intervals due to the statistical reliability of the time it takes for a certain fraction of element to decay. Atomic time: this relates to a precise and stable transition between energy levels within atoms, which occurs at extremely high frequencies, and are used to define the second in SI system. Atomic clocks are the pinnacle of modern timekeeping. Optical lattice clocks: these cutting-edge devices utilize grid of laser beam to trap and observe atoms. within even greater precision than conventional atomic clocks, achieving an accuracy of 10 to 18 seconds. They are still under development but show a great promise for future timekeeping standards. Planck time. On the theoretical scale, Planck time represents the smallest possible unit of time that is physically meaningful. According to our current understanding, it's the time it takes for a photon to travel at the speed of light to cross Planck's length. Atomic clocks are the most accurate timekeeping devices known, fundamental to modern technology and scientific research. Unlike traditional clocks that rely on mechanical or electrical oscillators, atomic clocks derive their exceptional precision from unchanging resonance frequencies of atoms, specifically the oscillations of electrons as they shift between energy levels. This principle, rooted in the laws of quantum mechanics, provides an extremely stable and consistent timekeeping mechanism. Fixed frequencies. The fundamental principle behind an atomic clock is that atoms of a specific element are identical and, when properly stimulated, will always absorb and emit electromagnetic radiation at the same unvarying frequency. This inherent and immutable atomic frequency acts as the pendulum or oscillator of the clock. Electron jumps. The electrons orbiting an atom can occupy different energy levels. When an electron jumps between these levels, it absorbs or emits a photon of a specific frequency. According to Wikipedia, this very specific frequency is the atomic resonance or clock transition frequency. Matching the frequency. Setting the time. If the microwave frequency precisely matches the atom's resonant frequency, or cloud of atoms, it causes a significant number of electrons within the atoms to jump between their energy levels. The maximum number of these jumps occurs when microwave frequency is perfectly tuned to atomic resonance. Feedback mechanism. The atomic clock employs a sophisticated feedback system. It monitors the number of atomic transitions and adjusts the microwave frequency until the maximum number of transitions occurs, effectively locking the microwave oscillator to the atom's resonant frequency. Counting the cycles. Once the microwave oscillator is precisely tuned, the clock simply counts the cycles of now stabilized microwave radiation. 1 second, by international definition, is precisely 9,192,631,770 cycles of microwave light associated with the hyperfine transition of cesium-133 atom in its ground state, undisturbed by external fields. Why atoms? Inherent stability. Unlike mechanical or quartz oscillators, atoms are not susceptible to manufacturing variations, wear and tear, or environmental factors like temperature or pressure fluctuations. All atoms of the same type are fundamentally identical. High frequency. The resonant frequencies of atoms, particularly in the microwave or optical range, are extremely high compared to mechanical or even quartz oscillators. This allows the measurement of very tiny fractions of a second, significantly increasing accuracy. Types of atomic clocks. Cesium clocks. Considered the primary standard, they are highly accurate and stable. Used to define international second. The U.S. Primary Standard Clock (NIST-F2) is cesium fountain clock. These clocks typically cool cesium atoms to nearly absolute zero using lasers, and launch them in a fountain to provide a longer time for interrogation with microwaves. Rubidium clocks. These are more compact and affordable than cesium clocks, making them popular in commercial and aerospace applications, including satellites used in global positioning systems. According to the National Institute of Standards and Technology, hydrogen masers. These clocks use hydrogen atoms and are known for their superior short-term stability, making them valuable in certain specific applications like radio astronomy. Optical clocks. These are the next generation of atomic clocks. They utilize even higher frequencies in the optical part of the electromagnetic spectrum, resulting in even greater precision, potentially losing less than a second over billions of years. They are currently a highly active area of research and are based on elements like strontium, aluminum, and ytterbium. In essence, atomic clocks harness the incredibly stable and predictable oscillations within atoms to provide the most precise timekeeping known to humanity. Their development has revolutionized areas from navigation and communication to scientific research, and ongoing research into optical and nuclear clock promises even greater accuracy and new applications in the future. Thank you for listening to this podcast. Until next time, curiosity adventures through the fields of science.